So under isomerism, we were discussing the optical isomerism. The last class we have completed the optical isomerism in tetrahedral geometry with monodentate ligands and also tetrahedral geometry with bidentate ligands. That to be in bidentate ligands in tetrahedral geometry, structurally unsymmetric ligands. What I given two ligands I have given. One is benzoyl astenato and salicyl aldehyde. We have discussed some boron and beryllium complexes with bidentate ligands, tetrahedral complex of beryllium and boron we have discussed. Now we will see now the coordinates number 6 in octahedral geometry, how this optical isomerism. Coordination number 6, octahedral geometry, octahedral geometry. So first we take octahedral geometry with monodentate ligands. Octahedral, I am writing like this, octahedral with monodentate ligands. Octahedral with monodentate ligands. First type let us consider types under this. First one, take Ma4B2 or you take Ma3B3. Either you take Ma4B2 or Ma3B3, both of these complexes with monodentate ligands. Either you take cis isomer or the trans isomer. Cis isomer and trans isomer of both of these complexes are found to be symmetric. We can cut into equal halves. Symmetric. So they are obeying all these symmetry elements, either plane of symmetry, center of symmetry, axis symmetry. These are symmetric complexes. Either you take cis or trans geometries. Therefore, these two models, these two are not exhibiting optical isomerism. So, no optical isomerism due to symmetric geometries. Because of cis and trans both are found to be symmetric, therefore no geometrical isomerism, symmetric geometries. Because these are symmetric, therefore no optical isomerism. Coming to the second, take now Ma2 B2 C2 you take plus or minus n. Let me give real example. You take one. Consider CO, take NS3 taken twice, and Cl2 let me write, H2 taken twice, Ma2 B2 C2 you consider. This is what the Cl2, therefore plus charge is enough to make it cobalt plus 3 to the complex. Recollect what we have discussed about this particular complex. For this particular complex, 5 geometrical isomers are possible I given, but out of these 5 geometrical isomers, now 3 are isolated I said. Theoretically 5 geometrical isomers are possible, clearly given already. Out of these 5 geometrical isomers, 3 are only isolated I said. Among this particular 5 isomers, the cis isomer is unsymmetric. I will write the cis isomer and I will show how it is optically active. See, only cis isomer found to be cis isomer unsymmetric. This can only exhibit optical isomerism, optically active. Only cis isomer unsymmetric. Let me write here instead of writing that one, let me say it is optically active. optical active. Let me show this particular cis and how this is optically active. Take CO, octahedral, right. We take this Cl and Cl cis and aqua, amine. You know, this is actually cis isomer. This cis isomer is optically active. Now, we can write one is D isomer to take, the other one L isomer. One is D isomer, the other one is what? L isomer. Consider first one as D, next L. See, for this, theoretically 5 isomers are possible. One of the cis isomer is what? It is unsymmetric complex. Therefore, that is optical active. Let me say this is both of these. Let us say one is D isomer. Second one is L isomer. D isomer and L isomer. Next model, let us take the next one, the second one, next third one, you see. M, A, B, C, D, E, F. M, A, B, C, D, E, F. All the 6 ligands are different. M, A, B, C, D, E, F. Plus or minus N. Take an example, real example. Take platinum. The bromide, chloride, iodide. Let me write NO2. Take one NH3, NH3 and P1. This is the complex. Recurrent in geometrical isomerism also I have given this particular complex. I said for this 15 geometrical isomers are possible, I said, out of which 12 are cis isomers and 3 are trans isomers. 12 are cis, 3 are trans isomers. But all these particular 15 geometrical isomers, those geometrical isomers are unsymmetric because no two ligands are identical. Then this particular complex cannot be cut into equal halves under any angle you take. Then this particular complex, no two ligands are actually identical, all are different from each other. Therefore, you cannot cut into equal half. Definitely, this particular complex, all the 15 geometrical isomers, whatever you say, those are unsymmetric complexes. Once unsymmetric complex is there, that will be active. Therefore, 15 geometrical isomers are possible, you said. See, I am writing 15 geometrical isomers. Geometrical isomers. Geometrical isomers. All are unsymmetric. Fifteen geometrical isomers unsymmetric, so all are optically active. All are optically active. Say once 15 geometrical isomers all are optically active means total number of optical isomers coming to be 30. 15 are D, 15 are what? L. So all are optically active. That is 30 optical isomers are possible. 30 optical isomers. 30 optical isomers. So 15 geometrical isomers, all are unsymmetric and all are optically active. 30 optical isomers. So total number of optical isomers possible for this particular is what you can say 30 optical isomers. Now, this is under octahedral geometry. only with monodentate ligands. Let us see next bidentate and monodentate ligands. Bidentate and monodentate ligands. So octahedral with bidentate and monodentate. Bidentate and monodentate. Types under this you take bidentate and monodentate, MAA taken twice, B2. BC. MAA B2 C2 plus or minus here. Next, instead of taking AA symmetric, you can also take unsymmetric bidentate. Yes, M AB taken twice, B2 plus or minus N. M AB taken twice, BC plus or minus. See, one thing is important here, in all these particular complexes, only cis isomers are optically active but not trans. Only cis isomers are optically active but not trans. Let us write that particular point here now. Only cis isomers are optically active. Only cis isomers are optically active but not trans. In all these cases, trans is not optically active, only cis is optically active. Let us take one by one how they are exhibiting optical isomerism. Take the first model, MAA B2, let me write. This MAA B2, CO, take En taken twice, Cl2 plus Cl2 plus. Let us write only cis isomer CO one ethylenediamine, second one take this as what? Say this as D isomer. So this is optically active mirror plane input, and take this next L isomer for this. So D isomer and L isomer, this cis isomer is optically active. I said trans is not optically active. Let us write a trans structure and let us see how it is optically not active, optically inactive. See, I am writing a trans for this. CL I am keeping in a trans position. This is what optically inactive. This is what trans, but this is what meso we can take. Meso not optically active. Meso not optically active. So getting a mirror plane, check it. Then you are getting what? A superimposable. Superimposable mirror image you are getting. Superimposable mirror image. Therefore, that is optically inactive. Meso compound is C. Similarly, you can also show for MAE taken twice, BC. It is more or less same. Instead of chlorine and chlorine, we can write Cl and Br. We can show for CC that is optical active and trans that is what? Not optical active. Let me show that one. MAE taken twice, B2. Now, MAE taken twice, BC. CBC, CLBR I write, CLBR. Now, let me write here cis only again, CLBR, yes, CLBR. So, this particular complex D you consider and that is what? L. And similarly, if you write for the trans is again optically inactive, let us say. Optically inactive, BR. So, like this, MAE taken twice B2 and again BC. Next, let us take MAE B2C2. And first only say MAA B2C2 plus or minus N. Let me write CO, EN you take, EN. Let me say H2O twice, Cl2. Right. This is B2C2 type. Let us write one cis complex for this. The monodentate ligand I keep in cis positions. This particular take this as D isomer. So put the mirror plane, then CO D isomer, L isomer, like this. Or M, AA taken twice, B2, next BC we are taken, MAA, then A2, B2C2, MAA, B2C2. All these cis isomers are optically active, as shown on the three models. Next, let us see. In some cases, octal geometry may carry two different bidentate ligands, two different bidentates and monodentates. Let us see the next. Two different bidentates and monodentates. So two different bidentate and monodentate ligands. monodentate ligands. This model, let me write one more way. A optically active complex with optically active ligand. A optically active complex with optically active ligand I am writing. See, optically active complex with optically active complex with optically active ligand. Optical active complex with optical active ligand. Look here. What is said? Two different bidentates. Take one is AA, two different bidentates, and let us write C2 plus. In this CO, one I write PN, one I write TN. PN and TN I am writing. Then Cl2 plus. See, optical active complex to optical active ligand. So this particular PN is optical active ligand. How you say this is optical active ligand? Let us check it the structure of PN. You know, CH3, 1,2-diaminopropane. This you see. This is carrying what asymmetric center. This particular ligand itself optical active, and the complex is also found to be optical active. So, optical active complex with optical active ligand. This is important to remember. For this, we write again optical isomers. Take the cis. Let us write one is PN and TN, CH2, CH3. This is PN. One is TN, take this as what D isomer, D isomer. Right next mirror image of this L isomer, same complex. CH2, CH2 and NH2. Also say one is D, the other one will be L. See. So octal geometry with monodentate we completed. Octal geometry with two different, with bidentates and monodentates, and with two different bidentates and monodentates. In that we are taking it as what a optical active complex which is carrying optical active ligand and optically active complex. Optical active complex with the optical active ligand. This is the best example under this. As we are taken, PN is what a optical active ligand, as it is carrying what asymmetric center. The ligand is optical active, but overall complex is also optically active. Next we see octal geometry with only bidentate ligands. With only bidentate ligands. But all these structures you have to practice once or twice. Otherwise, you cannot directly put in the examination wherever required. But once or twice you have to practice on the paper all these different models, whatever you give. Octadile with only bidentate. only bidentate ligands. Under this, let us write the first what types. Take this MAA taken thrice. Either it may be symmetric or unsymmetric. Bidentate ligand, it makes no difference. All are found to be optically active. Now, MAA taken thrice. MAA taken twice. BB, two different also you take, two different bidentates. Plus or minus N. Next, it may be unsymmetric bidentate. Let me write MAB taken twice, MAB taken thrice to take. Thrice. Next, MAB taken twice, BB. So, octal geometry with only bidentate ligands, either may be all same type of bidentates or all different types of bidentates. Two different types of bidentates or all are identical bidentates. All are found to be optically active. All are optically active. Optically active. Let us take this particular first one, MAA taken thrice. Next, MAA taken thrice. Let us see what is the real example on this. Now you take CO, EN taken thrice, you take plus or minus N. Plus or minus N. Let us write this particular model. How it is optically active. Octahedral. CH2, CH2, NH2. Similarly, one more. D isomer. Take the L isomer. For the same mirror image, right? So when you are saying D, the other mirror image you can say L isomer. One is D isomer, the other is what? L isomer. All the same bidentate ligands. Let us take two different bidentate ligands. Next, MAE taken twice, BB you take. Next one, the first model only you take MAA taken twice, BB. Two different bidentate. What example you can write? Take EN taken twice, C2O4 you take. Plus. See oxalate, one oxalate I given, one 2 or ethylene diamines, oxalate ligand, and 2 ethylene diamines. One, the second one, Take this as the D isomer. Next mirror image you write for this, that will be trans. Trans isomer, this is what D, and again what that is L, sorry. D isomer, the mirror image L isomer. One is D, the other is L. Take one is D, the other is what? L isomer. One is D isomer, L isomer. All are identical bidentates and two different bidentates. So all these complexes are found about optically active. Next, octal geometry with the exodentate ligand we take with EDTA. Octal geometry with exodentate ligand also found to be optically active. The next one. Type 2, let us consider this as type 2, right? Octahedral geometry with only binded that we have taken. Right, octal geometry with hexadentate ligand we write with hexadentate. Hexadentate ligand. Under this octal with the hexadentate ligand, take M EDTA. See, M EDTA is optically active. Take CO EDTA. CO EDTA is what? Optically active. How it is optically active? Let us put the diagram and see D and L isomers for this. Look here. It is a little difficult to draw, but you have to practice this particular. EDTA ethylene diamine tetrastato, 4 acetate groups, C double bond O. Next one, CH2, C double bond O. See, this is, you can consider this as what? D isomer. Say D isomer. Come on, write the mirror image for this. L isomer. For the same mirror image, right, that will be representing L isomer. Carefully you have to write this particular diagrams and you have to practice well. CH2 C double bond O. CH2 C double bond O. Next CH2 C double bond O. One D isomer, the other one is L isomer. D isomer and L isomer. See, MEDT, COEDT is what? Optically active. This is the optical isomerism in different complexes. With monodentate we have taken, with bidentate and monodentate, with two different bidentates, and again only bidentate ligands, that to be all same type of bidentates, two different types of bidentates, and this particular a complex with excidentate EDT ligand also exhibiting like this isomerism. So, this is the different types of isomerisms from the beginning: structural isomerism, stereoisomerism, different types were taken, all this. Next, let us discuss stability constants. Stability constants of the complex compounds we will discuss. Stability constants. Stability constants. Stability constants. See, most of the complex compounds are found to be stable. Then you take a complex compound, then it is found to be stable. Still, even though in aqueous solution it ionizes into a smaller extent. Smaller extent, you take a complex, I am writing on the board, Ag, NH3 taken twice, Cl you take. This once you are putting in aqueous solvent like water, ionizes to a smaller extent. To what? It is metal cation, ionizes to produce what? A metal cation and amine ligands. Amine ligands. Let me write, instead of writing this particular chloride, let me write this particular in a brief, easy way. Let me make it like this. AgNH3 twice plus this ionization in the aqueous solution like this. Let us write equilibrium constant for this particular equilibrium equation. Now, Ag plus NH3 square, then it is Az NH3 taken twice plus. This is the equilibrium constant for this particular K equal to Ag plus NH3 square, Ag NH3 twice plus. This K value is found to be experimentally, it is 1.6 into 10 to the power of minus 8, very less value. This particular K, we can consider what equilibrium constant for our convenience sake. Instead of saying this particular K as equilibrium constant, let us make it dissociation constant. Yes, equilibrium constant it may be, but for our discussion sake, let us consider this particular K as dissociation constant. The dissociation constant value, how much it is found? 1.6 to the power of minus 8. It is what? It is very, very lower value. 1.6 to the power of minus 8, it is what? Lower value. Means what do you understand? The dissociation constant is very less, you are saying. When dissociation constant is less, dissociation is less. Yes, a particular complex is actually dissociating very less. Out of some lakhs of this particular complex ions, only 10 or 20 are ionizing. What do you understand by this? Out of lakhs of complex compounds, only 10 or 20 are actually ionizing. Means you can easily say the most stable complex. Following. K is the equilibrium constant. For our discussion sake, let us consider K the dissociation constant. Its value is experimentally found to be, it is what? 1.6 10 to the power of minus 8. It is very less value. Means that particular complex undergoing very less dissociation. Less dissociation means the complex is more stable, therefore it is undergoing very, very less dissociation, therefore that particular complex is more stable. Now, the stability constant we can define in different ways. Let me say, first definition, stability constant. Stability constant definition, you see, stability constant. Stability constant. Stability constant is inversely proportional to dissociation constant. See what is said, dissociation constant is very less, stability is more. So stability constant is inversely proportional to dissociation constant. Next, there is also measure of metal ligand bond strength. Metal ligand bond strength you take. Metal ligand bond strength is very high, stability constant is very high. It also gives a information about strength of the bond between metal and the ligand. So bond strength. Bond strength. Greater the metal to ligand bond strength, greater the metal to ligand bond strength, greater will be the stability. Next, there is also measure of metal ligand bond formation. Rate of formation of the complex. Once rate of formation of the complex is more, take NL, let us take N. Rate of formation of the complex is more, that particular complex is also found to be stable. So stability constant inversely proportional to dissociation constant. It gives information about metal ligand bond strength and also gives information about rate of formation of a complex. If the rate of formation of the complex is more, stability is more. Rate of formation of the complex is less, stability less. Either the way we can define this stability constant. See, now let us discuss factors influencing stability constants. Factors influencing stability constants. Right. Factors influencing stability constants. Factors influencing stability constants. Mainly two factors we come across. First one, take nature of the metal cation. Here let me write one. Nature of the metal cation. Nature of the metal cation. Second one, nature of the ligand. Nature of the ligand. One is nature of the metal cation, second one is nature of the ligand. Under these two factors, first let us have a discussion about how nature of the metal influencing stability of a complex. Stability of a complex. First one, let us take nature of the metal cation. Under this, let us take first size and charge over the metal ion. Size and charge over the metal ion. Size and charge over the metal ion, the first one. Next, electronegativity of the metal ion. First one is size and charge over the metal ion. Second one, electronegativity of the metal ion. Third one, EAN of the complex, EAN. Fourth one, electronic configuration. Electronic configuration. Size and charge of the metal ion, electronegativity, EAN, and electronic configuration. This is the first one, size and charge. Remember, a metal cation is smaller size. A metal cation with a smaller size possesses greater charge density, then it will show greater electrostatic force over the ligand. Strength of the bond will be high. Therefore, a metal cation with smaller size possesses greater charge density, produce highly stable complex. See how? What I said, a metal cation with smaller size. Consider Fe plus 2 and Fe plus 3 you take. Yes, you can easily say Fe plus is what smaller in comparison to Fe plus 3. Let me write this is what this much bigger and this is what little smaller. And moreover, it is carrying what plus 2 charge. Yes, the charge density is what thin around it. Charge density is what thin around it. Charge density is thin. But here Fe plus 3 is what smaller in size, possessing greater charge density. it is plus charge density is very high, plus charge density around it is what thick. While the greater the charge density, it can easily show stronger electrostatic force on the negative ligand or any ligand, then strength of the bond will be high. Therefore, a smaller cation possesses greater charge density, it can show greater electrostatic force on the ligand, strength of the bond will be high. Therefore, a metal cation with smaller size possesses greater charge density, produce highly stable complex. Second one, electronegativity. What is electronegativity? The tendency to attract the donated pair of electron or the tendency to attract the bonded pair of electron towards itself. A more electronegative metal ion is there that is easily accepting the donated pair of electron from the ligand. Once it is easily accepting, the strength of the bond will be easily formed, and once the bond is easily formed, then we can say the strength of the bond will be high. Therefore, a more electronegative metal ion produce more stable complex. Suppose you take metal, the greater electronegativity easily accepts a donated pair of electron, and strength of the bond will be high. Therefore, it will be more stable. Greater the electronegativity of the metal cation, that can produce highly stable complex. Coming to next, EAN. Recollect again Sidgwick's theory, what we have discussed in the other classes. We have already completed that. EAN. Whichever the complex obeying EAN means the complex which is having EAN either 36, 54 or 86. 36, 54 or 86, that particular complex are found to be more stable. So, the complex which is obeying EAN, which is having EAN either 36 you take or 54 you take or 86 you take, such complexes are found to be more stable. Next, electronic configuration you take. Here we have to discuss electronic configuration. Now, generally, inner orbital complexes are more stable than outer orbital complexes. Inner orbital complexes are more stable than outer orbital complexes. Why inner is more stable and outer is less stable? Let us see. We have discussed many complexes, inner and outer, under applications of crystal field theory. Now, you know well now, consider 3D series. Suppose 1, 2, 3, 4. 4 shells are written. Now, once inner orbital complex, we are talking about 3D element to take. Example, we are taking 3D element, we are discussing this particular concept. Now, if you consider inner orbital complex, 3D orbital is involving. For 3D orbital involving, clearly you are observing the bonded pair of electron will be, this is the ligand, the bonded pair of electron will be near to the nucleus of the metal ion. Bonded pair of electron is near to the nucleus of the metal ion, more attraction force over the bonded pair. More attraction force over the bonded pair, and strength of the bond will be high. Therefore, a inner orbital complex producing more stable complex. Consider the outer orbital complex. Yes, outer orbital complex involving 4D orbital. You can clearly observing it is little away. So, this particular 4D orbital is involving the bonded pair of electron will be away from the nucleus of the metal ion, and less attraction force over the bonded pair. Less attraction force over the bonded pair, then strength of the bond will be less. Therefore, the outer orbital complex are found to be less stable. So, inner orbital complex are more stable, outer orbital complex are less stable. This is the concept about the influence, the stability constants influenced by the nature of the metal ion. These are the factors. Next, let us see the stability constant which are influenced by ligand nature. Next, we take nature of the ligand. Nature of the ligand. Under nature of the ligand, first one under this, size and charge over the ligand. Size and charge. Size and charge over the ligand. Field strength of the ligand. Field strength. field strength, pi accepting nature, pi accepting. Many are there. Let us discuss these two factors under this nature of the ligand. Size and charge of the ligand. A ligand with smaller size, take fluorodione, take iridione. A ligand with smaller size possesses again greater charge density. Once charge density is more, it can show greater electrostatic force on the metal cation, and strength of the bond will be high, therefore produce highly stable complex. See, smaller fluorodione, bigger iridione you take. It is smaller, then the negative charge density will be very thick, and here the negative charge density will be thin. Negative charge density will be thin. This is what thin negative charge density. Then it can show greater electrostatic force on the metal cation. Greater electrostatic force on the metal cation, and strength of the bond will be high. Once you talk about only halide complexes, order of stability of halide complexes, yes, the stability of fluoride complex is more stable than chloride. Chloride is more stable than bromide. Bromide is more stable than iodide. This is the order of stability of the halide complexes. Coming to field strength and pi accepting nature. Field strength and pi accepting nature. Recollect again, we have discussed the spectrochemical series. A strong field ligand and a weak field ligand we have classified. A strong field ligand is actually causing greater splitting of d orbitals, and a weak field ligand is causing lesser splitting of d orbitals. Whenever a strong field ligand is causing greater splitting, electrons are getting paid in the lower energy level, giving rise to a complex with a greater CFSE value. Greater CFSE, greater crystal field stabilization energy, that particular complex is found to be more stable. Once d order splitting is more, yes, that results in a highly stable complex. When d order splitting is less, that will be what giving rise to less stable complex. See what I said, a strong field ligand produce more stable complex than a weak field because greater splitting of d orbital. A strong field is causing what greater splitting of d orbitals. A weak field is causing lesser splitting of d orbital. Consider a d6 system you take, right? All the this is what you say T to Z. This is say easy. This is easy again. This is T to Z. T to Z and easy you take. Now, all the 6 electrons are entering into lower energy level. Then you talk about the CFSE of this particular complex that produces a complex highest CFSE minus 2.4 or minus 24 you take. Minus 24 dq of CFSE value it is gaining. Therefore, that particular complex is found to be highly stable. Next, pi accepting nature. Recurrent in the classification of ligands, I have given pi accepting ligands. Some of the ligands are actually capable of forming double bonds with the metal ion. First, they are donating a pair forming sigma, and again accepting a pair forming a pi. So, some of the ligands are actually capable of forming a double bond with the metal ion. Double bond, you can say double bond strength is more than single bond strength. Therefore, wherever we come across this particular pi accepting ligand, what are the pi accepting ligands? Some of the examples: carbonyl, nitrosyl, cyano, triphenyl, phosphine, bipi. Such ligands are there. They are forming a double bond with the metal ion, and such complex also found to be highly stable. What are the ligand? CO, carbonyl, nitrosyl you take, and cyano, triphenyl, phosphine, etc. Wherever this particular pi accepting ligands are there, they are forming double bond with the metal ion. Double bond. One is sigma, one is what pi. Such complexes are found to be highly stable because double bond strength is more than single bond strength. Easy concept about this particular nature of the ligands. First one is size and charge. Second one is what field strength and pi accepting nature. Next, third one we discuss chelate effect. Under ligands, chelate effect. Chelate effect to take. Let me write one more. Chelate ring size. Chelate ring size. Chelate ring size. Chelate effect. Generally, wherever chelate ligand or the polydentate ligands are there, that particular complex is found to be highly stable. This higher stability in comparison to the complex carrying monodentate ligands, that particular higher stability we call it what? Chelate effect. The complex with chelate ligands is found to be abnormally more stable in comparison to the complex which is carrying monodentate ligand. That higher stability we call it as what? Chelate effect. Why a polydentate ligand or a chelate ligand is producing a highly stable complex? See, it may be due to formation of rings around the metal ion. Formation of rings around the metal ion. Rings around the metal ion. What happens by forming the rings? Stability is increasing, as said. Next one, you see rings around the metal ion. It may be due to formation of rings around the metal ion. Second one, metal to ligand, all the bonds may not be broken simultaneously. May not be broken simultaneously. Now, suppose this particular complex you are heating to 100 degrees centigrade, you consider. For example, then one of the bond is breaking, with other bond still it is intact. So out of two bonds, one bond is breaking, other bond is intact. Suppose you are decreasing the temperature to 100 degrees to lower the temperature to 50 degree. Then the broken bond will reform and we are getting the complex. That means a polydentate ligand is not linked to metal ion with single atom. Many donor atoms of all may not split simultaneously. That is also maybe the reason for the higher stability. In addition to this particular two reasons, one what I said, rings formation. Second one, all the bonds between the metal and the ligand may not split simultaneously. Third one, what you can consider now, see third reason is a suitable reason you can consider why chelate complex are generally found to be more stable. Whenever a complex with the chelate ligands is produced, see nickel H2O taken 6, a +2 complex. This is what a complex with monodentate ligand. This is forming a complex with a bidentate ligand to take, bidentate ligand, ethylene diamine to take, bidentate ligand. Then in the direction of formation of the complex, whenever a complex with a chelate ligand is produced, the direction of formation of the complex, there will be increase in entropy. There will be increase in entropy. Increase in entropy. Delta S is increasing here. There will be increase in entropy. Now, either you say increase in entropy, you say, or whenever the complex with the chelate ligands is produced, the direction of the forming of the complex will be exothermic reaction. Yes, any product which is produced by exothermic process, that will be found to be highly stable. So, whenever a complex with chelate ligands is produced, the direction of the formation of the complex, there will be increase in entropy, or you say the direction of formation of the complex, that particular reaction is found to be exothermic. Exothermic product is highly stable. Therefore, compared to this particular complex, this chelate complex is found to be more stable. Coming to the next, chelate ring size. Chelate ring size. Now, chelate ring size generally you take, in general, a 5-membered chelate ring is less stable than a 5-membered chelate ring is more stable. A 5-membered chelate ring is more stable than 6-membered chelate ring, provided the chelate rings are saturated. Chelate rings are saturated. Now, suppose you are taking MEN complex to take, M-ethylene diamine. MEN complex. Then TN complex I am writing, look here, TN trimethylene diamine complex. MEN complex is more stable than what? TN complex, and this is 5-member ring, that is 6-member ring. This is the what order of stability. Next, once you talk about chelate ring size under, here 5-membered is more stable than 6-membered, provided both the rings are saturated. So this is what order of stability. Order of stability. Now we talk about a 6-membered chelate ring. A 6-membered chelate ring take. A 6-membered chelate ring is found to be more stable, provided 6-membered chelate ring is a resonance hybrid, unsaturated. See, I am writing MACAC. MACAC resonance, let us see. MACAC resonance. See, I am writing MACAC now. Acetyl acetylato complex. Plus or minus N. See this particular ACAC ring, you are clearly observing on the board, there are double bonds. There is a possibility of resonance like this. See next resonance structure, single bond, double bond, CH, C, double bond, right? Double bond, make it coordinate bond, minus N, plus or minus N, and it is what CH3. See, this is 5-member ring, more stable than 6-member, provided both the rings are saturated. But what I said, a 6-member ring is more stable than 5-member ring, provided the 6-member ring is unsaturated and resonance hybrid. If 6-member ring is unsaturated resonance hybrid, then that particular 6-member complex 6-member ring is more stable than 5-member ring. Therefore, would compare MEN and MTN. MEN is more stable. MEN is more stable. We compare MEN and MACAC complex. MACAC complex is more stable than methylene diamine. MACAC complex is more stable than methylene diamine. So we can write like this: ACAC complex is more stable than MEN according to this particular concept. This is what ring size. Next, number of chelate rings. Number of chelate rings. Next concept under the same nature of the ligand. Number of chelate rings. Number of chelate rings. One is the nature of the ligand under size and charge. Next, the field strength by accept nature and chelate effect, ring size, and number of chelate rings. Let us take this is what fifth, I hope. Number of chelate rings. Fifth effect. Now, suppose any one chelate ligand, any one chelate ligand which is capable of forming more number of chelate rings, that particular complex is found to be highly stable. What I am saying, a chelate ligand which is capable of forming more number of chelate rings, that is found to be more stable. Let me give now. Suppose you are talking about Cu H2O taken 4 times, you take plus 2. Cu H2O 4 times instead of H2O, let us write all same type. NS3 let me give, so good. CuNS3 taken 4 times. Next, CuEn taken twice. CuEn taken twice plus 2 and Cu dienurate. Diene taken twice plus 2 and Cu trienurate. Cu triene plus 2. Cu triene plus 2 it is. C1 is amine complex, ethylene amine complex, diene and trienurate. Order of stability we talk about. This is less stable than this. This is less stable than this. This is less stable than this. So this is what you say order of stability. Order of stability. Next, why you are writing this particular order of stability? How can you say? Let us see number of rings formed by single chelate ligand. Let us see number of chelate rings. Number of chelate rings by single chelate ligand. Single chelate ligand. So it is amine ligand on the monodendrite, no ring. But we talk about ethylene amine, 2 donor atoms are there, it can form only one ring. 2 donor atoms, one ring. See, number of rings by a chelate ligand equal to number of donor atoms minus 1. Number of chelate rings by a chelate ligand equal to number of donor atoms minus 1. So ethylene amine, 2 donor atoms, it can form only one ring. So it can form only one ring. And diene how many donor atoms? 3. 3 minus 1, 2 rings. Therefore it is what? 2 rings. How many donor atoms are there in triene? 4. 4 minus 1, we can say this what? It is forming 3 rings. Like this. More the number of rings, more the stability extent. How can you understand this? This is forming no ring. Means what? Only it is linked to the metal ion by single bond. Only one bond is there. To break this particular one bond between the metal and ligand, requiring less amount of energy. Here 2 rings. This particular ethylene amine is linked by 2 donor atoms or 2 bonds. Then breaking of this particular 2 bonds is requiring more amount of energy. Coming to diene. Diene is linked by 3 bonds. Diene is linked by 3 bonds. Breaking of 3 bonds is requiring more amount of energy. In the case of triene, diene is 3 bonds. And only single triene you take, it is linked to what? This particular metal ion by 4 donor atoms. 4 bonds are there. To break this particular 4 bonds, requiring more amount of energy. So number of donor atoms linked to the metal is increasing, number of rings are increasing, and to break that particular ligand from the metal requiring more amount of energy. Therefore this particular order of stability greater the number of rings formed by a single chelate ligand, that is forming highly stable complex, order of stability, and number of rings by single ligand. This is what the stability constants influenced by the nature of the ligands. Next we see importance of some ligands and complexes. Importance of some ligands and complexes in our daily life you take, or in practical chemistry and in biological chemistry. Take the first one, let me say DMG ligand. DMG is generally used in the detection and estimation of nickel. It is used in the detection and estimation of nickel plus 2 ion in practical chemistry. DMG ligand is used in the detection and estimation of nickel plus 2 ion. Then a nickel salt is converted into a nickel DMG complex. Nickel DMG complex. Many times questions appear on this. What is the hybridization of this particular complex? What is the geometry of this particular complex? What is the color of this particular complex? That you have to remember. So very, very important. The DMG ligand and the complex. It is actually square planar with the DSP2 hybridization. It is rose red. rose red or scarlet red in color. Rose red or scarlet red in color. So this is the importance of DMZ and the complex nickel DMZ complex. Coming to the second one. Consider EDTA. It's very important ligand. For many purposes we use this particular DMZ, this after DMZ next EDTA ligand. Standard EDTA solution, standard. See, standard EDTA solutions generally used in the volumetric estimation of calcium plus 2 and Mg plus 2. Volumetric estimation of calcium plus 2. Volumetric estimation. Volumetric estimation of calcium plus 2 and magnesium plus 2. Or you can also say estimation of hardness of water. Standard EDTA solutions are generally used the volumetric estimation of calcium plus 2, Mg plus 2, and also in the estimation of hardness of water. So standard EDTA solutions are titrated against either calcium plus 2, Mg plus 2 solutions or hard water. You can estimate what amount of calcium plus 2, magnesium plus 2 ions are there in the hard water. And this particular EDTA is also used. EDTA used in the removal of hardness. Removal of hardness. They also used in the removal of hardness of water. So standard EDTA solutions are used in the volumetric estimation of calcium plus 2, Mg plus 2, and also estimation of hardness. In the removal of hardness of water also we use. When EDTA you are adding to water the calcium plus 2, magnesium plus 2, forming this Mg and calcium EDTA complexes, and we can remove this particular complex from the water. Next, see, lead is a poisonous metal, a toxic metal. Anyhow, somewhat unknowingly or knowingly, suppose lead enters into our body, it shows its toxic effects in our body. For the removal of this particular toxic metal from the body, we use a complex. We use a complex. It is calcium disodium EDTA. This particular complex is used for the removal of toxic metal from the body. Unknowingly or knowingly, somewhat this particular lead, if enters into the body, it causes a lot of toxic effects or effects in our body. For the removal of, once we identify lead is there in our body, for the removal of this particular lead from the body, we use calcium disodium EDTA. Next, see, copper is required for our body, but in trace quantities only. If it, the copper amount in the body is becoming more, excess copper in the body again acts as what, toxic. Excess copper in the body acts as what, a toxic element. Once we diagnose that this copper is there in our body more than the required amount, then for the removal of this particular copper from the body, we use penicillamine ligand. A ligand penicillamine we use. A ligand penicillamine is used for the removal of the copper from the body because excess amount of copper in the body causes a disease known as Wilson's disease. Because Wilson's disease is toxic, therefore for the removal of this particular copper, then we use this particular penicillamine ligand. Next, in the electroplating, the electroplating of silver, electroplating of aramute, electroplating of aram, electroplating of copper. For the electroplating of silver and aram and copper, we use this particular complexes. Now, Na, Ag, Cn twice. This particular complex is used for the electroplating of silver. Similarly, in the electroplating of aram also, we use this particular complex Na, Au, Cn taken twice. For the electroplating of copper, then we use this particular complex. Remember, K3 Cu Cl taken 4 times. This is what copper 1 complex. These particular complexes are used for the electroplating of this respective metals: silver, gold, and again copper. Next, some more are there. We will discuss in hydrometallurgy. In hydrometallurgy, for the extraction of silver and gold, the complex used is Na, Ag, Cn taken twice. This particular complex is used for the extraction of silver. Extraction of silver in hydrometallurgy. Hydrometallurgy. Similarly, the extraction of gold also, same complex is used, but Rm complex. Same for the extraction of gold in hydrometallurgy. In hydrometallurgy, for the extraction of silver and gold, these are the complexes we use. See, nickel tetracarbonyl, you might be knowing this, one of the famous complex, nickel tetracarbonyl, used in Mons process. Mons process for the extraction of nickel. For the extraction of nickel, this particular complex is used by Mons process. Say cobalt complex, dicobalt octocarbonyl. Dicobalt octocarbonyl acts as a catalyst. Acts as catalyst in hydroformylation or in oxo process. This particular complex, dicobalt octocarbonyl, is used as a catalyst in hydroformylation or oxo process for the preparation of long chain alcohols. For the preparation of long chain alcohols. Long chain alcohols. So this is very important. Cisplatin we call. Cisplatin. Cisplatin is used as what a cancer drug for the curing of cancer. This particular complex we use. What is this particular complex? Cisplatin. Dichlorodiamines. Cis that to be. Cis-diamine dichloro. Cis-diamine dichloro platinum 2 complex. Only cis complex. Used in curing of cancer. It's very, very important to remember. Curing of cancer. You know well, this particular iron plus 2 complex, what you call as a hemoglobin you take. Iron plus 2 complex, hemoglobin. Hemoglobin, which involves in the transport of oxygen in our body. Hemoglobin, there in red blood cells. Involves in transport of oxygen. Transport of O2 in our body. Fe plus 2 complex, hemoglobin, there in red blood cells, involves in what transport of oxygen. 11 you take. Next one. A cobalt plus 3 complex, what you call cyanocobalamin. Cyanocobalamin, or you say vitamin B12. Vitamin B12. Cobalt plus is there in cyanocobalamin or vitamin B12. This is the cobalt complex, vitamin B12 or cyanocobalamin. It's in many ways useful for human life and other living beings, vitamin B12. These are some important complexes and some ligands which are important either practical chemistry or biochemical industries and in the form of complexes or ligands.